Hey, it's Mr. Lum, and this is your Unit 2 review practice answer key guide. Anyways, we're going to jump into it and solve some of these questions. If you know how to do it, skip ahead in the video and yeah. Anyways, which of the following, this first one right here, which of the following will cause the equilibrium to change from blue to green? In other words, that is a very fancy way of saying shift right. So we want to look at something that shifts right here. Now, so I'm going to go through all of them. We know that adding a catalyst does no shifting right here. This one right here that says adding some NaNO3. Na and NO3 are not into this equation. If we decrease the temperature, so if the temperature decreases, the reaction is going to be shifting left. Okay, and we're looking for something that's shifting right. That kind of leaves only this answer right here, adding NaBr. And you're probably wondering, well, what does NaBr do for this equation? Well, NaBr, the Na does nothing in the equation, but the Br, I know this is solid, but the Br is going to dissolve in water, and the Br is going to actually increase this Br right here. Remembering from some Science 10, NaBr is ionic, and that means it's composed of or made of Na plus and Br minus. And so when you add NaBr into a solution, that Br minus is going to increase the Br minus, and that'll make it shift right. So A is the answer. Okay, consider the following equilibrium. We have nickel plus carbon monoxide makes NiCO4. Which of the following will cause the equilibrium to shift to the left? Okay, we have some energy right here. This is going to be an exothermic reaction, and me personally, I like it when my energy is in the equation. Since I know that negative change in enthalpy means exothermic, that means we're going to have energy right here. So adding some carbon monoxide will make it shift right. Decreasing the volume, we only have one gas right here. And so if you decrease the, which of the following will cause the equilibrium to shift left? If you decrease the volume, you are increasing the pressure. And since pressure, this one's a gas right here, that'll make that go up, and that'll also make it shift right. Remove some NiCO4. If I remove this, it makes this go down, okay, and that makes it also shift right. And that kind of gives us our answer. Increase the temperature. If we increase the temperature, it makes the reaction shift to the left. And that's our answer right there. Okay. Consider the following equilibrium. Which of the following shows the relationship between concentration and time as a result of adding a catalyst? This one should be easy. A catalyst will increase the forward and the reaction rates equally and by the same amount, and therefore there will be no difference in the amount of reactants and products. Okay? Yeah. Consider the following equilibrium, and there it is. What is the equilibrium expression? Okay, so equilibrium expression is KEQ, is going to be the products, concentration of products over the concentration of reactants. Now, The important thing to remember is that it has to be the concentration of the products. So only things that have concentrations. This is a solid. So a solid does not have a concentration. And so that does not go into your KEQ expression. This is a gas. That does have a concentration. This is a solid. It does not have a concentration, so it does not go into your KEQ expression. This is a gas, so it will. So KEQ will equal the products, HI, concentration of HI. Now, there's a 2 in front of it, so that means this gets squared. That's a product, so it's going to be over the reactants, and that's going to be over H2S. That does not have a coefficient in front of it, so therefore it's just the power of 1. We try to find this on here, and we see it's A. Okay. At equilibrium, so it says at equilibrium, the concentration of CO, water, H2, and C is all of these things. It gives us the KEQ. Please find what the concentration of CO2 is. I'm going to write a KEQ expression. KEQ is the concentration of the products, CO2. Everything's gas here, so everything goes in the equation, unlike the question above. CO2, H2 over CO over H2O. I'm going to plug in all my values. KEQ is 5.0. I got that from right here. CO2 we're looking for. So I'm just going to write CO2 in there. H2, it tells us that it's 0.9. CO is 0.2, and H2O is 0.3. I solve for CO2. I go 5 times 0.2 times 0.2 on both sides, and then time by 0.3. So do that on both sides. And then I'm going to divide by 0.9 so that I isolate my variable. And I get 0.3333 molarity of CO2. Everything should be 2 sig figs because of everything up here is 2 sig figs so it should be 0.33. There's my answer right there. Consider the following reaction. Here are the relative concentration of CO2, CF4, and COF2. To reach equilibrium, is it going to shift left or shift right? So here's the KEQ of the reaction. We're going to do a practice KEQ, or in other words, a trial KEQ. So trial KEQ actually has the same formula as real KEQ. It's just a test on KEQ. So it's products, COF2, squared, because of the 2. Everything is gases here, over CO2, or CF4. Plug in my values. COF2 is 0.3 squared over CO2 is 0.5 times another 0.5. Trial KEQ equals, typing in 0.3 equals by We got 0.36. And so since trial KEQ is much smaller than real KEQ, trial KEQ wants to become bigger. Since trial KEQ wants to become bigger, we're going to need more products. So if we want more products, it's going to be shifting to the right. So we're looking at one of these answers, right or right. And the reason why is because trial KEQ is smaller than real KEQ, or in other words, trial KEQ is less than real KEQ. That one right there. Okay, I have a couple more questions right here. And my cat is on my computer. Come on. Okay. The equilibrium will shift to the left as a result of the addition of. This question's a little bit tricky, and we don't fully have all the knowledge, but if you remember back into some grade 10, Science 10 knowledge, you might be able to solve this one, and I'll show you how it's done. So the equilibrium will shift as a result of this. So we want the equilibrium to be shifting to the left. That's what we want. Okay. Now, how can we do that? Well, we can increase Cl minus. So you might be a very common person, a lot of people will say, oh, I'm going to choose that one because that'll increase Cl minus. Well, you know what? This is not ionically bonded, so it will not make Cl minus ion when you put it into water. So that's not a right answer. Okay. And some people might choose like this one right here, NaOH. This is also not a right answer. NaOH is ionic. It'll increase the OH, and this will make it shift right. Okay? KNO3 will do nothing. There's no K or NO3 or anything up in the above equation. Now this is a tough question. This one right here is an acid. It's nitric acid. It's on the back of your periodic tables. It'll say in the top right-hand corner, that's nitric acid. This is a base. Acids and bases like to react, and they form neutralization reactions. Remember that from grade 10? Anyways, it forms a neutralization reaction. So when you add an acid, it actually decreases or removes the OH here. So it decreases that. And that makes it shift left. And that's the answer. Moving on. KEQ expression. Okay. This is a liquid. This is a solid. Liquids and solids do not go into KEQ expressions. Okay. So KEQ then is going to be 1 over, we don't put nickel in there, we're going to put just carbon monoxide in there. Now, carbon monoxide has the coefficient of 4 in front, and so we have to put this to the power of 4, like that. Okay, and that gives us this as the answer. Okay, this one right here, we have what is COF2? So same kind of question as before. I'm going to write a KEQ expression. Everything is gases, so everything goes into the equation. And we're going to look at CO2. That's a bad C. CO2. CF4. Or COF2. This is squared because of the coefficient in front. Nothing else is squared. Plug in our values, it gives us KEQ. so KEQ is 2.00 equals CO2, gives us that, 0.05. Gives us CF4, which is also 0.05. And it says, what is this value? Okay. I'm going to skip a lot of the algebra, but I'll show you what I get. It turns into COF2 is equal to 0.050 times, this is a times right here, another 0.050 divided by 2.0 right there. There was a squared right here, okay, but I removed the square because I'm going to take the root of both sides. And that means I need to take the root of this side as well. So I'm going to plug that into my calculator to find what the concentration of COF2 is. So I'm going to go 0.05 times 0.05 equals, divided by 2 equals, take the root of that number, equals 0.035. So COF2 concentration, which is my calculator saying 0.035355. That's a molarity, of course. Everything should be 2 sig figs because these things are 2 sig figs. So this is your answer right here. That one. Consider the following equilibrium. Gives us KEQ. And it says that 1 liter container, which is kind of nice, so that when it gives you to you moles, you divide by 1 to get molarity. So it's an easy calculation. And it wants to say, which way does this thing shift? Shift left or right? So we're going to do a trial KEQ. So I'm going to type in trial KEQ. Trial KEQ is going to equal to the products HOCl squared, because of the 2 in front, over concentration of water, because it's a gas, and Cl2O. Everything is a gas here, so everything goes into our trial, our KEQ expression. So now we're looking at trial KEQ. After we calculate trial KEQ, we'll compare it to the real KEQ. So I don't know what trial KEQ is yet. So I'm going to take a look at HOCl, and it says it's 0.1. And that number is squared. And it also says that H2O is also 0.1. And it says that, oh, ClO2 is also 0.1. Well, that makes the math nice and easy. We don't even need a calculator. If you can't see it, what it's saying is that trial KEQ is equal to 0.1 squared over, this is the same as writing 0.1 squared. 0.1 squared over 0.1 squared. Trial KEQ is 1. That number is way bigger than KEQ, like a lot bigger. So this number needs to become smaller. So in order to become smaller, we need to make these numbers right here bigger in value, or we need to make this number right here smaller in value. What I'm trying to say is that we need less products, more reactants. Or in other words, more reactants and less products means it's a shift to the left. So we're going to be looking at shift to the left. And that's because trial KEQ is much larger than KEQ. That one right there. Okay, now we're into the written questions. It says consider the following graph for this reaction. And the temperature is increased at time 1 and equilibrium is reestablished at time 2. On the above graph, sketch a line representing of HI between time 1 and time 3. Okay. So let's look at this equation right here. It's a 1 to 1 to 2 ratio. Okay. Now, this value right here is x. I don't need to write x though, because I actually can calculate it. This value is going from 0.6 to 0.5. So this value is 0.1. This is going from 0.2 to also 0.1. So this is 0.1 change. So these ones decreased. This one right here, HI, is going to increase by 2x, or in other words, 2 times these values right here. So this is going to go up by 0.2. It changes between time 1 and time 2. So it's going to go like this, and then reach a new equilibrium between time 2 and time 3. So this is the right answer right here. I'm going to show you like close to right answers, and so like some people will draw like this, like that, but it's reaching equilibrium too soon. Okay, it reaches equilibrium when these other H2 and HI also reach equilibrium. So just make sure to draw it carefully. There, it stopped changing, and then it stays at equilibrium right there. Okay, so that's how your graph should look like, something like that. Calculate the value of KEQ after time 2. Okay, so KEQ equals HI squared because of the 2 there. Everything is gases, so everything goes into our KEQ expression. H2, we gotta learn to do better square brackets. H2 times I2. There's no squaring right there because there's a coefficient of just 1 in front. So therefore KEQ equals our new values, 1.0, 0.5, 0.1. So this is going to be 1.0 squared over H2, which is 0.5, and I2, which is 0.1. So KEQ equals 20. Yeah. Okay. And that should kind of make sense. Like, we're seeing a lot more products than reactants, and that's why we see a KEQ that's a little bit larger. But yeah. Okay. Now we have a big 4-mark question, so it's going to be probably a nice table. So a 1 liter container, which is nice for calculating molarity, is initially filled with 0.1 SO2 and 0.1 O2. At equilibrium, the concentration is 0.06. Calculate the value of KEQ. So I'm going to rewrite my equation like this: 2 SO2 plus oxygen and 2 SO3. I'm just going to do a double check make sure that everything goes into my KEQ expression. Gas, gas, gas. So we're all good. We don't have to eliminate anything from our calculations. And we're going to plug some values in, I guess. Okay, so it says initially we have 0.1 SO2. So 0.1 SO2 and 0.1 O2. Okay, and then it says at equilibrium, we're going to have 0.06. Okay, so this decreased right here. That decreased, and that means this is going to decrease as well. Now, how to go from 0.1 to 0.06? Well, it decreased by 0.04. That's how much it decreased by. Now, how much did this one decrease by, the SO2? Well, since it has a coefficient of 2 in front, it's going to decrease by twice the amount. So it's going to decrease by 0.08 is how much it decreases by. This one starts off at 0, and this one is going to be increase, because it's on the other side of the equation, and since it's going to increase twice as much as oxygen decreases, so this is going to increase by 0.08. So 0.1 minus 0.08, 0.02, and 0.08. Okay. I'm now ready for my KEQ. KEQ is going to be equal to SO3 squared over SO2 squared times oxygen to the power of 1, because there's no coefficient in front of oxygen except for 1. Calculate KEQ. KEQ equals SO3 at equilibrium, which is 0.08 squared over SO2, which is 0.02 squared, and oxygen, which is 0.06. Therefore, KEQ equals, type in my calculator, 0.08 squared divided by 0.02. And I get a value of 266.6666. Let's go 267, since everything up there is 3 sig figs. Okay, last question. It says a container is closed initially filled with equal moles of H2 and Br2. When equilibrium is reached, the HBr is 0.329 molarity. What was the initial concentration of H2? So this one is legit tricky, so let's take our time. H2 plus Br2 turns into 2 HBr. Everything is gas, so everything goes into our ice table, everything goes into KEQ. It says a closed container was initially filled with equal moles of H2 and Br2. It doesn't even tell me. It just says initially filled with equal moles. They're the same, but I don't know what they are. So I'm going to write X in blue. I don't know why. Okay, X is equal to X, so those are equal. It also implies that we filled the container with 0 moles of this stuff. Okay. Now, I wrote, it says equal moles. We'll assume it's like a 1 liter container, so this is molarity. So X and X is a molarity. It says at equilibrium, the concentration of HBr is 0.329. 0.329. Okay, that means it had to increase by 0.329. That means these ones decreased by half the amount. Okay, so 0.329 divided by 2 is 0.1645. Okay, it is 0.1645 because that is half of 0.329, and that is purely because this is a 2 to 1 to 1 ratio, or a 1 to 1 to 2 ratio. What's X minus 0.1645? Well, that's just X minus 0.1645, X minus 0.1645. I'm going to throw that in a KEQ expression. KEQ equals HBr squared over H2 times Br2. No squares or anything. So KEQ is going to be, I'm going to now plug in my values. KEQ is going to be 14.8. Equals 0.329 squared over, now H2 is going to be X minus 0.1645. Br2 is going to be the exact same thing. So I could simply write squared like that. Now, what I'm going to do is I'm going to square root both sides. So 14.8, take the square root of that, is 3.847. And so just to kind of like show you what I did, I took the square root of this and I took the square root of that right there. And so now this is going to be 0.329. I got rid of the square, okay, because I square rooted it. And that's going to be X minus 0.1645. Again, I got rid of the square because I square rooted it. And now I need to solve for X. So I'm going to times both sides by X minus 0.1645. And I'm just going to write all that stuff right there, just so you know where that's going. So it's going to be 3.847. Kind of ran out of room, just like 3.847 X minus, now I gotta go 3.847 times 0.1645. Just doing that on my calculator right now. And I get 0.6328. And that equals 0.329. Now, I'm I'm going to add plus 0.6328 to both sides. And I get now 3.847x is now equal to 0.9618. I solve for x. And how I solve for x is I'm going to be, I'll show you in purple, divide by 3.847 on both sides. And so I go 0.9618 divided by 3.847. I get 0.25. 0.25. Okay. Now, the question asks, what is the initial concentration of H2? Initial. Okay. This is the initial because here's H2. Initial is just listed as X. We just listed it as X. So this is the answer. 0.25 molarity is the initial concentration of H2. If it asked me, what is the final concentration of H2? I would have to subtract 0.1645. So the final concentration of H2 is 0.0855. Okay, that's the final concentration of H2. But we're not interested in the final. The question is just asking for the initial concentration. Okay, and that's it. There's your video answer key. Okay, I hope it helps. Yeah, okay.